Hello and welcome to my technology presentation on electromagnetic radiation, and then a few different things that we have been able to apply scientifically, especially in the medical field, as a result of the electromagnetic spectrum and electromagnetic radiation, and specifically the UV spectrometer, application of X-rays, and then expounding on the use of X-rays in computed tomography applications, also known as CAT applications. The electromagnetic spectrum was discovered by Heinrich Hertz in Germany. He was the first to send and receive radio waves. James Clerk Maxwell had mathematically predicted their existence in 1864. So between 1885 and 1889, as a professor of physics at Karlsruhe Polytechnic in Germany, he produced electromagnetic waves in the laboratory and measured their wavelength and velocity. He showed that the nature of their reflection and refraction was the same as those of light, confirming that light waves are electromagnetic radiation obeying the Maxwell's mathematical equations. Here is Hertz's experiment. As you see here, we have the induction coil, which produces the high voltage, which then creates a spark, which produces the electromagnetic waves as they would move in different spectrums. And here, the electromagnetic waves create an electric current in a resonator, producing a small spark in a spark gap. This is the electromagnetic spectrum. We have short wavelength frequency and high frequency to the right, and then a low frequency and a low wavelength to the left. We'll start at the right with gamma rays, also known as nuclear energy, is produced by the sun and certain unstable atomic nuclei here on Earth. Then we have X-rays. X-rays can pass through many substances. We know these from getting our X-rays taken at the doctor. Next, we have UV radiation, which is a component of sunlight that can cause sunburns or suntan, and it has enough energy to damage biological molecules, and in too much, it can cause cancer. Then we have visible light, which is seen in a spectrum. The purple is the shorter wavelength with the high energy, to the red, which is a longer wavelength with lower energy. And as we all know, different visible lights can change our retinas in our eyes as it adjusts to seeing the light. Next, we have infrared light, which is heat that we feel when we place our hand near a hot object. All warm objects emit this infrared heat. Infrared light, we know this from things such as night vision goggles. Then we have microwaves, which is used for radar and obviously in microwave ovens. It is efficiently absorbed by water and therefore heat substances that contain water. Radio waves, the lowest on the spectrum, is used to transmit signal for AM, FM radio, cell phones, television, and other forms of communication. As we sit here in our rooms right now, respectively, there is visual light, possibly UV rays, depending if you are from if there's a window in your room, infrared light from the heat you give off. There is microwaves as well. All these waves existing simultaneously in one room at the same time. Now that we have the basis laid out, let's talk about some applications. In this particular case, we're going to talk about ultraviolet wave or we're going to talk about UV waves. UV waves can be used to make a machine called a spectrometer. A spectrometer is a result of a discipline of science called spectroscopy. Spectroscopy is used in research, scientific research, industrial production, and quality control. A spectrometer is an instrument that measures the amount of light absorbed by a substance. An example of a spectrometer application would be, say, gauging the dilution or concentration of caffeine in a variety of drinks such as coffee, tea, soft drinks, or energy drinks. Spectroscopy, excuse me, is gauged from this equation right here. A equals ECL. A being the absorbance, E being the molar absorption coefficient, C being the molar concentration, and L being the optical path length. We will now take a look at a spectrometer and how these work. So say we're trying to figure out how much caffeine is within a substance. So we have the light source of how we're viewing our sample of caffeine. So we have caffeine in this tube right here. The light source will then go through the monochromator, which has this prism, and then through the sample solution, we have this I of O and I of T. The I of O is the incident light, and then after is called the intensity after it hits the example. Through this process, we're then able to see through a computer screen what it is trying to gauge. And like I said, it could be used to gauge a wide variety of substances. In this case, we're just talking about caffeine. Next, we're going to be discussing X-rays. We all recognize X-rays from going to the doctor. Here's some examples of some fractured bones. X-rays can travel through things that ordinary light can't because they're more energetic. X-rays are produced in a more energetic version of the same process. If you want to make X-rays, you simply fire a beam of high-energy electrons accelerated using high-voltage electricity supply at a piece of metal. This metal usually used is typically called tungsten. Then what is reflected back is neither light nor electrons, but a beam of X-ray from that tungsten. Generally speaking, the higher the voltage you use, the faster the electrons go, the more energetic they crash into the tungsten, and the higher energy of the X-rays they produce. We all know that some materials, such as glass and plastic, let the light pass right through them very easily, while other materials, such as wood and metal, do not. In much of the same way, there are the materials that allow X-rays to pass straight through them. There's other materials that stop them dead in their tracks. When X-rays enter a material, they have to fight their way through a huge amount of atoms if they're going to emerge on the other side. What really gets in the way is the electrons whizzing around about the atoms. The more electrons there are, the more they have a chance of absorbing the X-rays, and the less likely the X-rays are going to emerge from the material. X-rays will tend to pass through the material made from lighter atoms with relatively few electrons, but they're stopped in their track with heavier atoms such as lead. And this would explain why you usually have to wear a lead apron, and why your radiologist also wears a lead apron when they're taking X-rays of you, so they are not damaged and so you are not damaged. X-rays can be used to stabilize medical equipment, kill tumors and the treatment of cancer. And those two uses of X-ray is known as X-ray therapy. Next, we're going to speak about computed tomography applications, also known as CAT applications. Computed tomography medical imaging systems generate three-dimensional images of internal body structures using complex X-ray and computer-aided tomographic imaging techniques. As we can see, we have an image that goes through here, and then through the signal, it is then goes through a variety of channels through the X-ray process to get a more complex hold on what the process is that we're dealing with at the time. Modern CT images systems can generate images in any plane within the body by using a technique called spiral CT. In a spiral CT system, the patient is slowly moved in the center of a gantry while the X-ray source and detector rotate around the patient, also known as a CAT scan. Very high-speed computers are necessary to process the images collected in this manner. Sophisticated tomographic imaging techniques are used to produce the required image. What we're looking at right here is a liver sample. Here we have a normal liver taken through a CAT scan, and here we have an unhealthy liver. And as we can obviously see the difference in all the millions of lives that this has saved as a result of looking and using this kind of technology. CT has been the basis for interventional work, like the CT guided biopsy, as also seen here through the liver samples, and minimal nerve damage invasive therapy. CT images are also used as basis for planning radiotherapy cancer treatment. CT is also used to follow the course of cancer treatment to determine how the tumor is responding to the treatment. And that's all the time I have to discuss these very complex and in-depth processes of the applications of the electromagnetic spectrum. I'm sure you have some questions, and if you do have some questions, just please email me or leave a comment my YouTube channel, and I will do my best to respond to it. And I thank you very much.